Alrighty. We're gradually bringing everybody on board. Let's see. Can never remember how to add people. Oh, okay. That's weird. Okay.
Hi.
Okay, Janae, are you able to see me?
Yeah.
Okay, good deal. All right, let's make sure we're still recording. Yep, still recording. Okay. All right. Okay, Leah, are you the only one down there? Oh, okay. All right. Well, well, that's better than nobody, I guess. Okay. Finally, we're technologically ready to get going. Okay. All right. Okay. All right. So, our first homework is due today. A number of people have already turned in. The rest of you, so you can, well, if you're up here, you can just turn it in to my office, or to, if you're remote, you can go ahead and email it in whatever format is most convenient for you. And I will try to get these, whichever ones I receive, I'll try to have them all graded by next Monday. No promises. Okay. So, last time I had introduced the Lu Factorization. So A is equal to LU, where L is unit lower triangular, and U is upper triangular, since lower and upper triangular systems of equations are far easier to solve. So what I'm going to do now is step through an example of computing an LU factorization. So matrix will work with so one of those 4x4 cases where the numbers work out nicely, of course. Okay, and we'll also have the right-hand side vector, 5, 1, 22, and 15. Okay, so if we perform the following row operations, we have all these elements, these 6 in the lower triangle that we need to eliminate. So 6 row operations altogether. And here are the row operations we need. Now, it's easy to figure out by looking at the first column what the first 3 row operations are going to be. and that is, so since the ratio of these elements is 3, we have row 2 is equal to itself minus 3 times row 1. And then the next row operation will be row 3. So we're just going to keep starting from right below the diagonal and working our way down. Row 3 is equal to row 3 minus 4 times the first row. And then we have row 4 is equal to row 4 minus twice row 1. And that's going to eliminate all these elements below the diagonal in the first column. Now, that's going to change these elements down here, and just by looking at the matrix here, we can't really see what those row operations are going to be. You have to carry these out first in order to see what elements you need to eliminate down here. So at this point, you'll just take my, either carry out the operations yourself, or just take my word for it. The next row operation on this element here is row 3 is equal to itself minus twice R2, row 2, and that takes care of this element. And then this element ends up becoming, it's 0 now, but it ends up becoming non-zero as a result of the other row operations. So, oh, wait a minute. Second row, third. Sorry, this ratio is a 1 as a result of this element being updated. So the fifth row operation to work on this element down here, which is no longer 0 at that point, is row 4 is equal to row 4 minus 1 times row 3. Let's start row 2 rather. Okay, because we're in the second column, so we're using a second row to eliminate elements in rows below it. Okay. And finally, we have this element over here, which is going to be changed as a result of all this other work. So our final row operation is row 4 is equal to row 4 minus, and the ratio turns out to be 1 again, times row 3. And the result of all this, after we perform all these row operations, we get an upper triangular matrix U. And that matrix is, okay, 1, 2, 1, minus 1, 0, minus 4, 1, 7, 0, 0, minus 2 and 1, 0, 0, 0, minus 1. So all these row operations produce this matrix. But each of these row operations can be represented by a unit lower triangular matrix. So for example, I can represent this row operation, row 2 is equal to row 2 minus 3 times row 1, by an elementary row matrix that is unit lower triangular. So the only row operation, since we're taking row 2 and subtracting 3 times row 1, we put a minus 3 in the 2, 1 position, and everything else in the lower triangle is going to be 0. Okay. So I can do this with each of the other row operations. So basically we're taking 6 elementary row matrices and multiplying A by them on the left in sequence, starting with this one, and then continuing with the elementary row matrices for these other 5 operations to get this in upper triangular form. Okay. So now what I can do is these elementary row matrices, by multiplying together, we can combine them into one matrix that takes care of the first column, another one for the second column, and then one for the third column. So now I can write out what those matrices are going to be. That'll produce the Lu factorization.
Hey, still a lot of
Oh, sorry, what?
the other girl that Skype's in, she's not here anymore. I don't know what happened.
Oh. Let's see if there are any.
She got disconnected or...
Ooh. Okay. That's a problem. Okay, am I still recording? Yes. She's still online. Hello. Not answering. Okay. Okay, well, I guess you'll have to watch the video. Okay. So, the idea is, using notation I introduced last time, if I let A1 be equal to A, so then A1 multiplied on the left by M1, M2, M3 is equal to our final upper triangular matrix, U. So each of these matrices works on the appropriate column. So M1 is equal to, well, it's a product of unit lower triangular matrices. So the first one I wrote out before, so I'll just label them as E1, E2, E3. So to save time, any blank spaces in these matrices are just zeros. So the next matrix that works on the third element in column 1 has a multiplier of 4. And then the third matrix, working on the fourth element in column 1, has a multiplier of 2. So multiplying all these together just basically superimposes these multipliers on one another. So we have -3, -4, -2. So this is M1. So this takes care of the first column, makes all those subdiagonal entries 0. And then the matrix that works in the second column is a product of only 2 elementary row matrices. Both have a multiplier of 1, and are working on the second column. Actually, I have them backwards. This one first, because we're applying from right to left. Then this one. And you multiply those together. So this works on the 3-2 element. This works on the 4-2 element. So I'll call these E4 and E5, corresponding to the 4th and 5th row operations I had on the previous board. So that'll be this matrix when you multiply them together. And then finally, there's only one row operation that works on the only element to be eliminated in the third column, row 4, and that's this matrix right here, which is also E6, corresponding to the 6th and final row operation. So, so what happens is, if I take these matrices, M1, M2, M3, and move them to the other side of the equation, then I have A, which is also A1, is equal to M1 inverse, M2 inverse, M3 inverse times U. But these are inverses of unit lower triangular matrices, which are also unit lower triangular. And when you multiply them, that's still unit is your L in the Lu factorization. And L, L is in unit lower triangular, and all the multipliers without the minus signs go in here. So we have 3, 4, 2, 1, 1, 1. And everything else is zeros. Okay, I just heard something going on Skype-wise. Ashley, you still there?
Yeah, I'm good.
Okay. I think I just got a message from Janae. Okay, that's Janae. She'll watch the video. So.
Okay.
Okay. So we're good. All right. All right. Okay. So we see from the Gauss elimination process, just performing row operations gives us U, and then recording the multipliers that we use along the way, what multiple of each row we're subtracting from another row, recording those multipliers in the interesting portion of L in the Lu factorization. Okay, so that takes care of the Gaussian elimination part, but then for solving a system, we now have to apply these same row operations to the vector B if we're going to be solving AX equals B. So any questions about the Lu factorization and where that comes from? All right, so we have this vector B from our system AX equals B. So we're solving Ly is equal to B. So that would mean that Y is, of course, L inverse times B. But from a way to find L on the previous board, in terms of M1, M2, and M3, L inverse is going to be multiplying from right to left. So M3 is applied, M1 is applied first, then M2, then M3. So in other words, Y is obtained by applying the same row operations to B that were earlier applied to A. And when we apply those row operations to this particular vector, what we get is 5, 1, 1, 3. So as far as our process of solving AX equals B is concerned, first thing is A is equal to LU. We factored that. Now we've solved Ly equals B. So that's the second step of the process. The third step of the process, we solve Ux is equal to Y in order to solve AX is equal to B. And for that, we just use back substitution. So I had it up earlier. The matrix U is so that's that matrix there. So now what we'll do is start from the bottom row and work our way up. So x4 is going to be y4 divided by u44. So y4 is going to be 3, and then u44 is equal to -1, so we just get -3 in that case. X3 is going to be y3, and then we have to take the term corresponding to this entry here and move it to the other side. So we're subtracting it off, so -2 times, actually I'll write out in terms of the entries, u34 times y4 divided by u33. So these are the formulas that you can see from the back substitution algorithm would need to be used. So we just go ahead and work that out. So 1 minus 1 times -3 divided by -2. So we get -4 over, write that down right. Oh, that's weird. Oh, okay, yeah. What? Okay. All right. I thought I made a mistake in my notes, and no, I hadn't. Okay, and then as we see from running this back substitution algorithm, that with each, as we go up the rows, we got to subtract off more and more terms. So u23 y3 minus u24 y4 all over u22, so that would be 1 minus 1 times y. Ah, dang it. These are supposed to be x's. So what I was putting for numbers was right, it's just I was using the wrong symbols to refer to them. u23 times x3, which is -2, minus u24 times x4 all over u22, which is -4. Okay, so 2 is 3, it's 21, it's 24 over 4 is -6. Okay. And finally x1, so that'd be y1 minus. So now we're going across the rest of the first row of u. So that's u12 x2 minus u23 x3 minus u24 x4 divided by u11. So so again, subtracting off 0, 1, 2, and then 3 terms, and that's what causes the back substitution process to be of order n squared operations for an n by n matrix. So we'll have y1, which is 5, and then we'll have -2 times -6, -1 times -2, plus 1 times -3, all over u11, which is 1. Okay, 17, 19, 16, so we get 16. So the solution of our system, ax equals b, which is also a solution at ux equals y, is we just read off these numbers backwards. So 16, -6, -2, and -3. Okay. Now, one thing to point out about the patterns in the indices that you see here, but like I have u34 x4, or down here u23 x3. So notice I'm sorry, but I keep messing these up. Okay. In each case, if you look at first this computation of x3, and then we have only one element with row 3. Here we have all elements row 2, and then the column index keeps increasing. And notice that the column index matches the element of x that we're multiplying with. Here again, the row stays fixed. That's how a column is taken, because that's what's supposed to happen. And then the column index matches the element of x that we're taking. What fundamental matrix algorithm has that kind of a pattern in the indices that we've seen before? Where the row index stays fixed, and then the column index matches bingo, yes, matrix vector multiplication. And that's what we're doing, because we have matrix vector product right here, and we're just moving terms over to the other side in order to isolate the elements of x. So once I wrote down properly, then it could be apparent. Okay. This is what I get for having class at the end of the day. Okay. Well, at least the notes are right most of the time. Although, as you'll see later, not all the time.
Dr. Lanford,
Yes.
for your equations where you say, like for x3, you have u3 4 times x4. What is x4? Is that
Okay.
so? Is that my y?
No. Because notice, well, this is why it's important to start from the last row and work our way up. So,
Oh.
yeah. So once we compute x4, we use the, yeah.
Okay.
Okay.
Okay. Thank you.
Okay. All right. Okay. Now, let's see. Okay, because I'm going to need it later, I'd written the algorithm for Gaussian elimination or LU decomposition last time, and we're going to need that again because I'm going to make little changes to it as needed. Okay, actually, I'm going to put it at the far side of the board, just so other stuff doesn't get in the way. All right, so you'll recognize the Gauss elimination algorithm, but I want to address specifically storage. Okay, so we use J as a column index, counting columns from 1 to n. And then I'm going to deliberately leave a little space here. We don't need yet, but we will later. And then within each column, I'm going to loop over rows, starting in the row below row J, and keep going all the way to the end. And then I compute my multiplier. So that's Aij divided by Ajj. And then I carry out the row operation. So k is equal to j plus 1, j plus 2, all the way to column n. So Aik is equal to itself minus Mij Ajk. Yep. Now, before when I wrote out this algorithm, I also put a line here to apply row operations to B. That's covered later in forward substitution, so I'm not going to put that in here now. But what I'm going to do instead is, this is just for storage considerations, not the actual algorithm. I'm going to set the Aij element, because Aij is what's meant to be eliminated by that row operation. So now there's just a 0 that's going to be there. But I'm not going to treat it as a 0. I'm actually going to take my multiplier and put it in that spot, because I'm not using that spot for anything else. It's available storage space. So all I'm doing here is storage of the interesting part of a matrix L. And I say the interesting part because the only thing that's interesting about L is the elements in a strict lower triangle below the diagonal. The diagonal is all ones, and above it the diagonal is all zeros, so it's not interesting to us. So the idea is you feed in A into this algorithm, all of A gets overwritten. The upper triangle is overwritten by the result of the row operations. The lower triangle is over, and the diagonal too. The lower triangle is overwritten by the multipliers. So then all of it is useful afterwards for solving Ly equals B, you use the lower triangle. And then for Ux equals Y, you use a diagonal in the upper triangle. So everything gets used. Okay. So now we have a algorithm for computing LU factorization, provided that the LU factorization actually, well, sorry, let me move out of the way for anyone who's, okay. So now we have, if I ever do that again, just tell me to move out of the way.
Okay.
All right, because I can pontificate from anywhere. So as long as the LU factorization is guaranteed to exist, as long as we never have a problem with this denominator AJJ ever being 0, this will work for us. And so we can do A equals LU, Ly equals B, and Ux equals Y. But how do we know whether that's going to happen? And if it does happen, what can we do about it? So now I'll take some time to address essential questions about existence and uniqueness of the LU factorization. So we'll just do a slight pan to the left there. Okay, so the first question is about existence. Under what circumstances does the LU factorization even exist? It does not always exist forever. Just because a matrix is invertible doesn't mean it's going to have a LU factorization. Okay. Fortunately, it is fairly simple to state a condition under which it does exist. Okay. So if I have an n by n matrix A, I'll write out a few entries here. All right. So I'm going to define the leading principal submatrices as the submatrices of A that you get by taking the successively larger upper left blocks that are square. So the leading principal submatrices. So I'll write it this way. A1 is just a number, a 1 by 1 matrix, A11. A2 is a 2 by 2 matrix. It's just the upper left 2 by 2 block. And then you keep going from there. So for instance, the A3 would be the upper left 3 by 3 block. And so on. So now in more MATLAB-like notation, AK is going to be rows and columns 1 through K. So it's going to be a K by K matrix. All right, so those would be leading principal submatrices. From that, I can define the principal minors of A. I'll use M for this. So MK is equal to the determinant of AK. So we can take the determinants of each of these leading principal submatrices, and then finally AN would be all of A itself. So what we can say is the Lu factorization exists if and only if all of these principal minors are non-zero. Right, for k going from 1 to n. So, for instance, that would require that A11 must be non-zero. Otherwise, you could not even eliminate elements in the first column. Suppose this is non-zero, but then this matrix A2 has a zero determinant. What would happen in that case is you're able to eliminate elements in the first column with no problem. Then you move to the second column, and that denominator, that your A22 that you're going to use as a denominator for your multipliers, is actually going to be the stem from determinant to this matrix. And so if this is a singular matrix, you're going to be dividing by 0. So as long as your minors are all non-zero, then you're fine. The Lu factorization will actually exist. I should mention that suppose the matrix A is symmetric. Now this gets to some things that only some of you will be familiar with depending on your background. If a matrix is symmetric and all of the principal minors are actually strictly positive, we can say something more. The matrix is then said to be symmetric, positive, definite, which we'll get into a bit later on. Actually, that came up in 419. I don't know if that rings a bell. Because I actually had you compute those. Okay. So that settles the question of existence. And for matrices, so what happens is, for a matrix to be invertible, we only need the last minor to be non-zero. But to have LU, we need all the minors to be non-zero. So in the case where this is not true, we'll have to work around it using row interchanges, which I'll get into shortly. But first, I want to handle the other essential theoretical question about the Lu factorization, and that is uniqueness. So if a matrix has an Lu factorization, is there only one Lu factorization? Well, let's suppose that there are two. So suppose A has an Lu factorization L1U1, and that is equal to a second Lu factorization L2U2. Well, all of the factors, both L's and both U's, have to be invertible if A is invertible. So I can move these to the other side as I need to. So I can, for instance, multiply on the right by U1 inverse. So I have L1 is equal to L2 U2 U1 inverse. And then I can also move this L2 to the other side. I can multiply on the left by L2 inverse. So I have L2 inverse L1 is equal to U2 U1 inverse. Now, in terms of triangularity, what kind of matrix do we have on the left side?
Lower triangular.
Lower triangular, and what else is true of it?
It's unit.
Unit lower triangular. Okay, what about the right side?
Upper triangular.
It is upper triangular. If the matrix is both lower and upper triangular, it is diagonal, like came up in the homework. So both matrices must be diagonal, but this matrix is diagonal and unit. So what does that mean? It has to be the identity matrix. So if L2 inverse L1 and U2 U1 inverse are identity, what can we conclude from that? So if we look at like this equal identity, what happens if you rearrange that?
What are we trying to find something out about?
About how L1 and L2 relate to one another. So if you say okay, so actually, just focus on this one right here. If you rearrange that, what do you get? U1 equals U2, because I can multiply both sides by U1. And so I get, and the same thing over here. So L1 equals L2, and U1 equals U2. So the conclusion is that the Lu factorization, if it exists, actually is unique. And we have an algorithm that produces it in those cases. So. But this way we can rule out if there's some other algorithm that happens to produce the Lu decomposition, it would have to be the same thing. Okay. Can't imagine how any other way of going about doing it, but that's, well, it's kind of moot now because it's unique. Okay. So any questions about the existence and uniqueness matters? Okay. So now we can start dealing with the central problem of what if the Lu factorization does not exist? What can we do about it? It will turn out that even if the Lu factorization does exist, for numerical purposes, that might not be enough for us. Okay. So now we get into pivoting. Okay. All right. So here are two potential pitfalls with the Lu factorization as we have it now. So first, what if the multiplier is undefined due to the diagonal entry being 0? But the other problem is in the main step of Gaussian elimination, so AIK is equal to itself minus the multiplier should mention, this is how you point out a pattern of the indices of matrix vector multiplication in back substitution. Here we have product of two entries. Notice the column index of the first matches a row index of the second. So this is what we see in matrix multiplication. So it makes sense that we would have this combination of indices here. Okay, so what can happen is, keep in mind, all of this is being carried out through floating point arithmetic. And whatever entry we have here, this AJK, is already affected by whatever row operations were performed in the past. So this element is going to have some round-off error in it that's accumulated over time. So the problem in this step as it's written is, if the multiplier is quite large, then what happens is the error that we've already accumulated in AJK can be significantly amplified. And that is going to cause serious round-off error contamination in the AIK element that we're now updating. So in other words, we don't want these multipliers to get out of hand in terms of size. If there's some way we can limit their growth, then we can limit this propagation of round-off error from one row operation to the next. So as a result of this, we can say that Gaussian elimination as is, just as I wrote it over there, is numerically unstable. Okay. Now, for some historical perspective on Gaussian elimination, back in the 60s or so, when numerical linear algebra was first coming about, when a lot of innovations were being made, Gauss elimination had already been around for a long time, but this is the first time that computers were really making use of it. But that's because that's when we first had computers. And there was a lot of concern about round-off error and about this numerical instability. And certain people took it upon themselves to try to analyze what would happen through the entire process of Gauss elimination and the accumulation of round-off error. One researcher actually concluded that the instability in Gauss elimination was so bad that it should not be used. Then Jim Wilkinson, who was one of the gods of numerical linear algebra, especially for the eigenvalue problem, he did a much more careful round-off error analysis, which actually is in the notes. I'm not going to cover it because, trust me, you'll cry. It is awful. I would have Stanford students just writhing in their seats from it in pain. It's just ugly. But you can read it if you want to. But what he proved was, under right circumstances, the remediation of this problem here with the large multipliers, that Gauss elimination actually could be made numerically stable. That it was possible to achieve some containment on the round-off error, and therefore people felt comfortable using Gauss elimination. And that was a significant turning point in numerical linear algebra, because what would we have done if we decided, oh, Gauss elimination, no, we just can't use that? That almost happened. So that would have been pretty interesting if one could go back in time and screw all that up and see what people would do differently for solving systems of equations. Maybe we would have done a lot more for iterative methods. I don't know. But people have to be really careful about these analyses, because one analysis reaches the wrong conclusion, and then Wilkinson comes along and gives the right conclusion. And there are certain things about the nature of Gaussian elimination that are still unknown, open questions about how bad this round-off error gets.
Well, people wouldn't have used Gaussian elimination, would they have used Lu Factorization? I know you might have to have, like a symmetric positive matrix.
Yeah, because at least in that case, you have some more guarantee of stability, but that's a real good question. What could you have done? Or maybe we would have said, oh, we just won't bother solving system equations. We'll just what? Because it's a pretty fundamental task. Okay. So for the solution of both of these issues lies in pivoting, which just refers to row interchanges. But then the question becomes, how do we change the rows? Because there is some choice there. So I'll talk about a couple strategies for making row interchanges, and then I'll incorporate that into this algorithm that I have over here that still has a blank space in it. As you can see from that blank space, the change is not going to be very much. I guess what people could have done was they could have formed A transpose A, which is symmetric positive definite, and then yeah. So, but then there's a downside to that of loss of information. Maybe people would just put up with it. So, yeah, because you're squaring your condition number. And, yeah. Lived in dark days. Okay. All right. So here are many pivoting strategies. I'll just mention a couple to give you an idea as to the flexibility you have. All right. The most widely used is called partial pivoting. So what you do in partial pivoting is before you eliminate entries in a certain column J. So at this point, you've already worked in your previous columns. You come to your jth column. AJJ might be 0 or near 0. You go ahead and swap row J with row P, and the meaning of row P is that, okay, so the element A, so row P column J is equal to the maximum so you look for the largest entry in this column, starting from a diagonal on down. Above the diagonal, you don't care about. So of all the elements you could choose to swap row J with, you look for a large element in that column, and that tells you which row you swap with row J. So if AJJ is already the largest in that column, you don't do anything. Okay. Now, so as a result of this, your ij entry of your matrix L from your LU decomposition, which is just the mij multiplier, so that would be aij over ajj, is guaranteed to satisfy that it is less or equal to 1 in absolute value. Because you're making sure that after you do the swap, you compute your multipliers, this denominator is larger than any of the potential numerators because of how what you've chosen to put there. So that contains the growth of the multipliers, that contains the propagation of a round-off error. Okay. Now, you're searching for the largest entry within a column. So in your first column, you have to look at all the entries, all n of them. For a second column, you have to look at n-1, and then n-2, and so forth. So as a result, you're doing a fair amount of comparisons. But what is the cost of doing these comparisons? Order n to the what power? If you're looking at n entries, then n-1 and n-2 all the way down, what's the total complexity of just searching through these entries? So you're adding up n plus n-1 plus n-2 and so forth. It's order n to the what? Okay. What's the sum of the first n integers? Yeah, so it's order. Yeah, so the dominant term in that is yes. Yeah, order n squared comparisons, and that's okay. That's negligible because the overall cost of Gaussian elimination is 2/3 n cubed operations anyway. So this is well worth it to go to this trouble of finding the right element to swap with. So you can have a situation where the LU decomposition actually exists, that you will never get a zero diagonal entry throughout the process, and it's still a good idea to do this because you're limiting the propagation of round-off error. Okay.
Dr. Lambers.
Yes.
Is it still the same cost since you're not doing any floating point arithmetic? You're just moving stuff around. I mean, is it still the same computational time?
The thing is, you don't only think in terms of floating point arithmetic. So you're simply a floating point comparison, and there's still an overhead to that.
Okay.
Yeah, yeah, there's still a circuit involved. In fact, one thing that we are still neglecting is just memory management, moving things around. That communication cost, as we go to more elaborate algorithms, is something to think about too. Okay. All right, so that's partial pivoting, and by far that is the most often used. The other pivoting strategy I'll mention, and this will explain why this is called partial pivoting. The other one is called complete pivoting. And what you do in complete pivoting is you not only swap rows, you also swap columns. So that AJJ is set equal to the maximum of AIK for I and K between J and N. So in other words, you're not just looking in that one column J, you're looking at the whole rest of the matrix from, so you forget about the first J minus 1 rows and columns, that whole block, you're searching to find the largest element, and then you'll swap rows and columns as needed to move that element, that largest element, into the JJ position, and then carry out your row operations from there. And you do this for each column. So initially you're scanning the whole matrix. Then you're scanning the whole matrix except for the first row and column, then first 2 rows and columns, and so on. So as a result of this, now your multipliers will be even smaller than what you would get from partial pivoting. But what is the complexity of the comparisons in this case? If you're scanning the whole matrix and then sub-matrices that it gets smaller and smaller.
What's the notation of the minute?
I'm sorry, what?
J is less than or equal to.
Oh, J, I and K, both. So I have 2 indices. Both are between J and N.
Yes.
So what do you think for comparisons?
We have n and then n minus 1.
Well, that was for this case. But now you're looking at the whole matrix first, and the whole by matrix, and then everything but the first row and column. So almost the whole matrix, and then down steps there. So what? Yes, it's cubed because you're adding up squares. N squared, n minus 1 squared, n minus 2 squared. So the formula for that is less well known. It's the sum of first n squares is n times n plus 1 times 2n plus 1 over 6. So it's order n cubed comparisons. Now that's not so negligible. That's the same order of complexity as the whole of Gaussian elimination. So, so people think twice before doing that. This does significantly stabilize Gaussian elimination even more than partial pivoting does, but most people have decided that partial pivoting, what that gives you is acceptable. And considering that it gives you this at least, and the overhead is far, far less. Okay. But I mentioned, like typical software packages, you're allowed to choose what kind of pivoting you want to do. Okay. It has been proven that complete pivoting causes Gaussian elimination to be what is called backward stable. That it's not possible for the entries of U to grow exponentially. So that's one thing that people pay attention to. In U, the matrix that results from Gauss elimination, how big do those entries get? Because again, that can cause the amplification of round-off error. But they don't get so big when you're doing complete pivoting, especially. It means that the entries do not grow exponentially in U. Okay. Now, whereas with partial pivoting, the entries can grow, like if you have an n by n matrix, they can grow by a factor of 2 to the n minus 1. That's like a pathological case that's contrived to make that happen. So it doesn't really, it tends not to happen in practice, but that's why some people choose to do complete pivoting anyway. Because they want to be really, really sure. Okay. So now, how does this affect, okay, well first of all, okay, yeah, I'll switch boards. How does this affect the Gaussian elimination process? Because what we had before was we start with A, and we keep multiplying on the left by these elementary row matrices that eliminate elements. But now, in between, we are swapping rows. And for this discussion, I'll just keep it to partial pivoting. So we're only swapping rows and not columns. So now, we want to see how the LU decomposition or factorization with pivoting, and we'll just keep it to rows. There are variations of partial pivoting that may give you more flexibility choosing a rows. Like maybe you don't need to limit the multipliers to 1. Like maybe you want the multipliers below a certain threshold. And I'll explain when we get to banded matrices why that might be important. Okay, so the point is we're just swapping rows. So what happens is you start with A, and then you multiply on the left by what is called a permutation matrix. I'll talk about those momentarily. And then you eliminate entries. Then you permute again. If nothing happens, these permutation matrices are identity. But we have to be prepared to interchange rows at every step of the way. And finally you get to your last entries that you're eliminating. And the result of that is your upper triangular matrix U. Now, permutation matrix, I'll give an example. So here is basically you take the identity matrix and you swap rows of it. So here I've swapped the first 2 rows of identity. So multiplying by a matrix by this on the left swaps rows 1 and 2. Also, okay, I'll call this P. One property of permutation matrices is that they're all orthogonal. P transpose P is equal to the identity matrix. Okay. Also, the determinant of P is going to be 1 or minus 1. It depends on how many, how many interchanges are made. For instance, if the determinant of this matrix is minus 1. Because you took identity that has a determinant of 1, you swap 2 rows. One swap causes a sign change. And if I had swapped 2 rows and swapped 2 more rows, that would have flipped the determinant back to 1. Okay, dang, almost out of time. Now, from this, though, it becomes quite inconvenient to get an LU factorization out of this. So this equation can be rewritten. So you start with A, and then you take all the row interchanges and you apply them up front. And then you have your elimination matrices. However, these matrices are not necessarily the same. I do have it written that way in the notes. That is actually an incorrect statement. So these M tildes, these M's, they are closely related, but they're not exactly the same. And we get U from that. So what happens is the LU factorization, in order to take all these and move them to the other side, I get P times A is equal to L times U. So A does not have an LU factorization necessarily. P times A does. So PA is just A with all row interchanges performed. And these row interchanges are intended to make sure that the resulting matrix with swap rows has non-zero principal minors, so that the LU factorization actually exists. Okay, so how do you get this in the actual algorithm? Because it seems strange that if you could just take all the row interchanges, that you don't know what you're doing until the end. But then you can look this way, you're making all the row interchanges up front and getting this LU factorization that you computed along the way. It turns out it's very easy to account for this in the algorithm. Now P, I'll write down P is a product of all the permutation matrices that you used to carry out the row interchanges. Okay, so I'll finish by showing you what happens in the algorithm that I've left there on the board for some time, and then I can point you some MATLAB code that I've posted on the site. Yeah. Okay, so just need to look over here. All right, so how do we account for pivoting right here in the algorithm? So what you do is you, I choose a row P so that the element in row P column J is equal to the maximum. So I'm choosing the, so now I'm adding partial pivoting. Okay, and we look at all the rows from row J down to the bottom. We find the largest element, so now we're going to swap row J and row P. And what we do is we swap all of row P and row J in A. Now, the reason why I'm emphasizing swapping all of this, because keep in mind, at this point, we've already worked on certain columns, eliminating entries, and we've stored multipliers in those entries we've left behind. So, when I'm saying swapping all of the rows, all of these rows from columns 1 to n, you're swapping the matrix entries you have yet to touch, and you're swapping the multipliers you already stored. As long as you swap everything in a consistent manner, your LU factorization will work out correctly. Now I'm going to point you some code on the site that's on the lectures page. Look for LU pivot.m. So you'll find it there. I think it's actually in the February 25th entry, so for Wednesday's class, because I'm a little bit ahead. So if you look there, you'll see how this is implemented, including the pivoting, in code. And what I do is, you'll see the one line where I swap row J with another row. But the other thing I'll do is I need to record what row change I made. And the way I do this in MATLAB is actually quite simple. I don't want to create a whole permutation matrix, because permutation matrix is all zeros except for n ones. kind of like identity matrix. So what I do instead is I make a vector of indices from 1 to n. And as I interchange rows in A, I interchange indices in this vector. So the final vector, after all this is done, contains a record of how all the rows were swapped. So then that gives me a compact, storage efficient representation of P. So now if I want to rearrange those rows of anything else, then I have an easy way of doing that. And actually in MATLAB syntax, it's really easy to do. So I'm out of time now. So I will explain how pivoting impacts the rest of solving AX equals B on Wednesday. Any questions?
I have one.
Yeah.
So, I don't understand. So, would you be able to like interchange rows 2 and 1, and then you would undo yourself at a next step or something?
Actually, what you do is instead of undoing, you're kind of like doubling down, because actually here's the easiest way to see it. If I am starting with AX is equal to B, but I need to interchange rows, I apply that to both sides of the equation. PAX is equal to PB, and then PA is Lu factorized. So instead of undoing, I'm going to apply the same row interchanges to B, and then I proceed as before. So you're swapping both sides of the equation in a consistent way.
Okay. But you're doing P a bunch of times, right? So
Yeah.
no, or it's P everything. P's all your rows.
Yeah. P records all of them. Yeah. The capital P does. Yeah.
Okay.
All swaps. All swaps.
Yes, all the swaps.
Dr. Lou,
Yeah.
when I tried to print, what I had in all my code and stuff in MATLAB, it wanted to print 24 feet.
It what?
It wanted to print 24 feet.
Oh, wait, did you ever print matrices along the way, or large vectors?
I think I had, I don't know, I don't honestly.
Can